Have you ever stopped to think about those elements? You know, the ones kind of tucked away at the bottom of the periodic table, the ones you maybe don't hear about so much.
The F block.
Exactly. Turns out they're actually vital for loads of things, from like the screen on your phone to nuclear power. A bit mysterious maybe, but really crucial.
Absolutely. They punch way above their weight in terms of applications.
We'll welcome everyone to the deep dive. This is where we take complex scientific stuff and, well, we try to make it engaging and clear.
And today, you've handed us Chapter 23 from a classic textbook, Shriver and Atkins Inorganic Chemistry. The chapter's called The F block Elements.
Right. And our mission, our deep dive today, is to unpack all this dense material. We want to clear up the technical terms, describe the structures without needing pictures, and importantly, highlight the surprising roles these elements play in your world.
Yeah, the goal is to give you a solid understanding without, getting totally overwhelmed by the details.
So we'll be exploring the two main groups, the lanthanoids and the actinoids. We'll look at what makes them unique, how we actually find and separate them.
Their physical properties, those cool optical and magnetic behaviors, and then dive into their chemistry compounds, structures, even some cutting-edge uses.
Okay, let's dive in. First things first. What defines this F block family?
So fundamentally, we're looking at two series of elements, 14 in each series, and they're defined by the way their electrons fill up the available energy levels, or orbitals. Specifically, they're filling the 4 and then the 5 orbital.
Okay, 4 and 5N. These are quite deep inside the atom, right?
Exactly. You can sort of picture them as being buried beneath outer electron shells. That has big consequences for their chemistry, as we'll see.
So two series. Let's start with the first one, the 4F series.
Those are the lanthanoids. They start with cerium, element 58, and go across to lutetium, element 71. We usually lump lanthanum, element 57, in with them too, because its chemistry is just so similar.
Lanthanoids. Got it. I think I've heard them called lanthanides before.
Yeah, you often hear lanthanides, but chemists prefer lanthanoids now. It's a subtle thing, but ionide usually implies a negative ion, like chloride, and these are metals forming positive ions. So lanthanoid avoids that confusion.
Time to sense. And what about the name rare earth elements? Is that right? Are they rare?
Ah, that's a classic misnomer. It's stuck historically, but most of them aren't actually rare at all. Cerium is about as abundant as copper. Even thulium, one of the less common ones, is found in similar amounts to iodine.
Really? So not rare. Any exceptions?
Well, there is one, promethium PM. That one is genuinely rare because it has no stable isotopes. It only exists as radioactive forms. But for the rest, rare is definitely misleading.
Good to clear that up. Okay, so that's the lanthanoids. What about the second series, the 5 elements?
Those are the actinoids. They start with thorium, TT element 90, and go up to lawrencium, LR element 103. And again, we usually include actinium element 89 with them.
And these are different from the lanthanoids, you said.
Very different in one key respect: radioactivity. While the lanthanoids are mostly stable, the actinoids, especially from americium onwards, are intensely radioactive and often synthetic. We only made them in labs.
Wow. Okay. So studying them must be incredibly challenging.
Hugely challenging. A lot of what we know about the later actinoids comes from experiments done on like micrograms of material, or sometimes even just a few hundred atoms at a time. It's incredibly difficult work.
So we have this contrast then. The lanthanoids, relatively stable, chemically quite similar across the series,
Remarkably uniform in many ways.
versus the actinoids, which are radioactive, harder to study, and show more chemical variety.
Exactly. That radioactivity and the behavior of their 5 electrons makes the actinoids much more diverse chemically than the lanthanoids. It really sets the stage for two quite different stories.
Okay, that's a great overview. Let's focus in on the lanthanoids first then. You mentioned their uniformity, but also their utility. It seems like a paradox.
It is a bit, yeah. Their chemistry is dominated by that +3 oxidation state, which makes them behave very similarly. But subtle differences and their unique electronic properties unlock all sorts of applications.
So where do we actually find these lanthanoids? Are they just lying around?
Not exactly. They're mainly found mixed together in certain minerals, often phosphate minerals like monazite sand or xenotime. They aren't usually found as pure elements.
And if they're all mixed up and chemically similar, separating them must be tough.
That's the major challenge.
Yeah.
Because they mostly exist as Ln3 plus ions of similar size, traditional chemical separation methods often don't work well.
So how do chemists tease them apart?
Well, there are a few tricks. For cerium and europium, we can use redox chemistry. Cerium can be oxidized to C, which behaves differently and precipitates out. Europium can be reduced to U, which also allows separation.
Okay, but what about the others, the ones that stick stubbornly to +3?
For those, we need more sophisticated techniques. On a large scale, liquid extraction is used. This involves using complexing agents molecules that bind the lanthanoid ions dissolved in an organic solvent. These agents have slightly different affinities for the different Ln3 plus ions, allowing gradual separation as they move between the aqueous and organic layers.
It's complex.
It is. And for really high purity, like for electronics or lasers, they use ion exchange chromatography. The mixed lanthanoid ions are passed through a column packed with a special resin. The ions stick to the resin and are then washed off selectively, usually with a solution of a complexing agent. The subtle differences in how strongly each ion binds allow them to be collected separately.
Like a very precise filtering process based on their chemical stickiness.
That's a good way to put it, yeah. Once they're separated as compounds, getting the pure metals usually involves electrolysis of their molten halide salts, like the chloride or fluoride.
Okay, so we've got them separated. You mentioned they're not rare, but they are useful. What are their general properties, and where do we encounter them?
Physically, they're typically soft, silvery white metals. They tend to be quite reactive, especially with air or water. They aren't great conductors of heat or electricity compared to metals like copper.
And the applications. You mentioned steel.
Right, mish metal. It's
Yeah.
basically a commercial blend, mostly cerium, lanthanum, neodymium, praseodymium. Adding it to steel acts like a scavenger, reacting with impurities like sulfur and oxygen. And it also improves the steel's strength and workability. It's also used as the flint in cigarette lighters.
Ah, okay. What about their more high-tech uses? Optics.
Oh, yeah, their optical properties are fantastic. Because of those unique electron energy levels, they absorb and emit light in very specific, sharp wavelengths. Europium compounds give brilliant reds. Terbium gives greens essential for phosphors in displays and energy-efficient lighting.
And lasers.
Absolutely. Neodymium, Nd, samarium, SMM, holmium Ho, erbium R, Ytterbium, Y ions of these elements are doped into solid materials like YAG crystals, yttrium aluminum garnet to make powerful lasers. And YAG lasers are workhorses in industry for cutting and welding, and also in medicine, like for eye surgery. Erbium lasers are used in dentistry and skin resurfacing.
And glassblower goggles, you mentioned that earlier.
Yeah, neodymium oxide is added to the glass. It strongly absorbs the intense yellow light emitted by hot sodium in the glass, protecting the glass blower's eyes without darkening everything else too much. Pretty clever.
It really is. And the magnets. I hear neodymium magnets are incredibly strong.
They are phenomenally strong. Alloys like neodymium iron boron and Nd₂Fe₁₄B or samarium cobalt SmCo₅ are permanent magnets far stronger than traditional iron magnets. They're essential in miniaturizing devices. Think headphones, computer hard drives, microphones, electric vehicle motors, wind turbines, even those little magnetic toys.
Wow. So, okay, steel, lighting, lasers, magnets. Quite a portfolio. Now, you mentioned a key trend that underpins their chemistry, the lanthanoid contraction. What's that about?
Right, this is fundamental. As I said, they're very electropositive, strongly preferring the +3 oxidation state. The lanthanoid contraction describes a gradual decrease in the ionic radius of these Ln3 plus ions as you move across the series from lanthanum, La3 plus, to lutetium, Lu3 plus.
So they get smaller. Why?
It's because as you add protons to the nucleus moving across the series, you're also adding electrons to the 4f orbitals. But these 4f electrons are really bad at shielding the outer electrons from the increasing positive charge of the nucleus.
Ah, the shielding effect again, or lack of it.
Exactly. The nuclear charge pulls the outer electron shells more tightly inwards, causing the ion to shrink. There are some subtle relativistic effects involved too, apparently, but the poor shielding by the 4f electrons is the main driver. It's a steady, predictable decrease.
And this shrinking has consequences.
Big time. It influences their coordination numbers, the strength of their bonds, and importantly, it's the basis for separating them using methods like ion exchange, because smaller ions interact slightly differently with ligands and resins.
And you mentioned they are hard Lewis acids.
Yeah.
What does that mean chemically?
Lewis acids accept electron pairs. Hard Lewis acids prefer to bond with hard Lewis bases, typically small, highly electronegative atoms like oxygen or fluoride, which hold their electrons tightly. This preference explains why lanthanoids are often found naturally in phosphate with oxygen or fluoride minerals.
Okay, mostly +3, but you hinted at exceptions. When do they adopt other oxidation states?
It happens when they can achieve an especially stable electron configuration by doing so. Think of empty, F0, half-filled F7, or completely filled F14, F orbitals as being particularly stable states, kind of like noble gas configurations. Cerium is a classic one. C3 plus has one F electron, F1. It can be oxidized to C4 plus Ri, losing that electron to achieve an S0 state. This makes C4 compounds strong oxidizing agents. Europium is another key example. U3 plus is F6. It can be reduced to UU2 plus SR, gaining an electron to reach the stable half-filled F7 configuration. So U compounds are quite stable.
Any others?
Samarium, SM2 plus, and ytterbium, YB2 plus, also have significant chemistry, but they are strong reducing agents, readily reducing water. There are rarer cases like praseodymium or terbium reaching a +4 state under very strong oxidizing conditions, often in solid oxides, again aiming for that S0 or F7 stability. But COPA and U2 are the most important deviations from +3.
Fascinating. Let's shift to their electronic spectra and magnetism. You said their absorption bands are sharp.
Yes, very sharp and relatively weak compared to, say, d-block transition metals. This goes back to those buried 4 orbitals. Because they're shielded by the outer 5s and 5p electrons, they interact very little with the surrounding ligands or the environment.
So the energy levels don't get jostled around much.
Pretty much. The electronic transitions between F orbitals, F transitions, happen at very specific energies, giving sharp lines. They're also technically forbidden by certain quantum mechanical selection rules, which is why they're weak. Compare that to dan-di transitions in transition metals, which are broader and more intense because the dandles stick out more and interact strongly with ligands.
And this leads to their colors and use in lighting.
Exactly. The weak absorption gives pale colors to many Ln3 plus salts, like praseodymium compounds appearing green because they absorb in the blue and yellow. But the emission spectra can be very strong. When you excite an F electron and it falls back down, it can emit light very efficiently. This luminescence is characteristic of the specific ion.
Like europium red and terbium green you mentioned.
Precisely. They are very strong emitters, which is why they're so valuable as phosphors in lighting and displays. And it's this efficient light emission that powers those NdYAG and other lanthanoid lasers.
What about their magnetism? Is that unusual too?
It is quite different from typical transition metals. In many d-block ions, the magnetic contribution from the electron's orbital motion around the nucleus is effectively canceled out or quenched by the ligand environment. But for lanthanoids, those buried 4-alpha electrons behave almost like they would in a free, isolated atom.
So both spin and orbital motion contribute.
Yes. Their magnetic moments depend on both the electron spin and the electron orbital angular momentum. You actually need a more complex formula involving something called the Landé G factor to calculate it accurately. It makes their magnetic behavior very distinct and often very strong.
Okay, let's talk structure. How do these large Ln3 plus ions arrange themselves in compounds?
Their large size is key. Compared to ions like iron 3, Ln3 plus ions are significantly bigger. This means they can accommodate more surrounding atoms or groups called ligands. So they typically show high coordination numbers anywhere from 6 up to 12 neighbors is common.
And the shapes they form.
Because the orbitals are buried and don't really dictate shape like orbitals can, the geometry is mostly determined by simply packing the ligands around the central ion to minimize repulsion. This leads to a variety of complex polyhedral shapes, often not the simple tetrahedral or octahedral shapes you see with smaller ions.
What about simple compounds like oxides or halides?
They form a range of binary compounds. Oxides like Ln2O3 are common. Sulfides like Ln2S3 are used as pigments. Halides show varying coordination. LaF3 has 11-coordinate lanthanum, while LCl3 has 9-coordinate lanthanum. Even hydrides, LNH2, LNH3, and nitrides, LNN, exist. Some lanthanoid carbides are even superconductors.
And complex oxides. You mentioned YA laser.
Right. Their stable +3 charge and predictable size make lanthanoids perfect for incorporating into complex oxide structures. Perovskites, like LaFeO3, are one example where changing the lanthanoid can fine-tune electronal properties. Garnets, like YAG, yttrium aluminum garnet, are another. Yttrium Y3+ is very similar in size to later Ln3+ ions, so you can easily substitute neodymium into the YAG structure to make the laser material.
You also mentioned NMR shift reagents. That sounded really useful.
It's a fantastic technique. Some lanthanoid complexes, particularly those of europium, praseodymium, or ytterbium, are paramagnetic. They have unpaired electrons and act like tiny magnets. If you add one of these complexes to a sample you're analyzing by NMR.
Nuclear magnetic resonance.
Right. The magnetic field from the lanthanoid complex interacts with the nuclei of your molecule, especially the protons nearby. This interaction shifts their resonance signals in the NMR spectrum, spreading them out.
So it makes complex spectra easier to interpret.
Exactly. It increases the resolution, helping chemists figure out complex molecular structures, even distinguishing between mirror image molecules known as enantiomers. Really powerful tool.
Okay, one last area for lanthanoids.
Yeah.
Organometallic chemistry. Bonding to carbon, is that different too?
Very different from D-block organometallics. Because the orbitals are buried and don't participate much in bonding, and they lack accessible d orbitals for the kind of back bonding seen with transition metals, the bonding is primarily ionic or electrostatic. Sterics, the size and shape of the ligands, also play a big role.
So rules like the 18-electron rule don't apply.
Nope, not relevant here. They tend to favor ligands that are good electron donors, like cyclopentadienyl CP anions. Compounds like LNCP3 were some of the first ones made. They generally don't bond well to pi acceptor ligands like carbon monoxide, which are staples of D-block chemistry.
But they can still do interesting chemistry.
Oh, definitely. Some lanthanoid organometallics show surprising reactivity. For example, certain lutetium compounds can activate the very strong carbon-hydrogen bonds in methane, which is chemically quite inert. And they are also used as catalysts in polymerization reactions like Ziegler-Natta catalysis for making plastics.
So, the lanthanoids. Remarkably consistent +3 state, subtle size changes driving separation and properties, unique optical and magnetic behavior, and surprisingly diverse applications.
That sums them up pretty well. A fascinating group.
Okay, but now we need to tackle the other side of the F-block coin, the actinoids. You've already flagged them as being more diverse, more complex, and significantly radioactive. Let's brace ourselves.
Right. If lanthanoids are about predictable uniformity, actinoids are defined by their variability, especially the earlier members of the series.
What's the fundamental reason for this difference?
It really comes down to the 5 orbitals compared to the 4 orbitals. In the early actinoids, thorium, protactinium, uranium, neptunium, plutonium, the 5 orbitals are spatially more extended. They stick out more from the atom.
Okay, so they're less buried than the 4.
Exactly. This means they can participate more directly in chemical bonding, along with the nearby 6-pin and 7s electrons. Uranium, for instance, has an electron configuration suggesting it can use up to 6 valence electrons for bonding. This accessibility of multiple electrons leads to a much wider range of oxidation states compared to the lanthanoid's dominant +3.
So instead of just +3, they can be +4, +5, +6.
Even +7 in some cases for neptunium and plutonium under specific conditions. The early actinoids show this rich redox chemistry. However, as you move further along the series, past americium, the +3 state does become progressively more stable, more lanthanoid-like in that sense. But the radioactivity also gets much more intense.
You can visualize this stability using Frost diagrams, right?
Yeah.
The textbook mentions them.
Yes, Frost diagrams are useful graphical tools. They plot the relative free energy of different oxidation states versus the oxidation state itself. The lowest points on the plot represent the most stable states in aqueous solution, and the slopes between points tell you about the tendency for redox reactions. They really highlight the complexity for elements like plutonium, which can have multiple states coexisting.
And does this difference in orbital behavior affect their spectra too?
It does. Actinoid electronic spectra, particularly the F transitions, tend to be broader and about 10 times more intense than lanthanoid FF transitions. That greater interaction between the 5 orbitals and the ligands causes this.
And other transitions are possible.
Yes, you also see transitions involving electrons moving from 5-5 to 6-apart orbitals, and importantly, ligand-to-metal charge transfer, LMCT transitions, where an electron effectively jumps from a ligand orbital to a metal half orbital. It's an LMCT transition that gives the uranyl ion, UO2+, say, its characteristic bright yellow color.
Ah, the uranyl ion. That sounds important. Does it have other interesting properties?
It's strongly fluorescent. If you shine UV light on many uranyl compounds, they emit a striking green-yellow light. This was famously used in uranium glass or Vaseline glass in the past, which glows under black light. It's less common now due to the radioactivity, obviously.
Right. Okay, let's talk about the big 2 actinoids that are studied most. Thorium and uranium. Why are they more accessible?
It's purely down to radioactivity. Both Thorium, specifically thorium-232, and uranium, mainly uranium-238 with a bit of 235, have isotopes with extremely long half-lives, billions of years. This means their radioactivity is low enough to allow handling and study using fairly standard chemical laboratory techniques, albeit with precautions.
Unlike the later ones, what's thorium chemistry like?
Thorium is actually quite straightforward compared to uranium. It almost exclusively exists in the +4 oxidation state in its compounds and in solution. Th4+ is a large ion, so it typically has high coordination numbers like 8 in thorium dioxide, THO2, or thorium tetrachloride, THCl4, and can go even higher in complexes.
And uranium? More complex.
Much more complex. Uranium commonly exhibits +4 and +6 oxidation states, but +3 and +5 states are also known and important. The chemistry changes significantly with oxidation state.
How so?
Well, take the chlorides. UCl3 features 9-coordinate uranium thread. UCl4 has 8-coordinate uranium fourth in a polymer structure. Uranium-6 forms UCl6, which is a simple 6-coordinate octahedral molecule, so coordination number tends to decrease as the oxidation state increases.
And uranium hexafluoride, UF6, that sounds familiar.
Yes, UF6. It's a volatile solid sublimes directly to gas at around 57 degrees C. This volatility is absolutely crucial for the nuclear industry because it allows for the separation of uranium isotopes.
Separating 235U from 238U, how does volatility help?
Because the only stable isotope of fluorine is fluorine-19, the only difference in mass between 235UF6 and 238UF6 molecules is due to the uranium isotope. It's a small difference, but using techniques like gaseous diffusion, or more commonly now gas centrifugation, these molecules can be separated based on that tiny mass difference. That's how you enrich uranium for reactors or weapons.
Fascinating. And the uranyl ion you mentioned earlier, UO2
Yes, the uranyl ion. It's a linear OuO2+ unit. It's exceptionally stable and forms a vast range of complexes, usually with additional ligands arranged around the uranium atom's equator. Its chemistry is central to the PRX process, the main method used for reprocessing spent nuclear fuel to separate out uranium and plutonium.
Okay, what about organometallic chemistry for these two? Similar to lanthanoids.
Similar in that bonding is still largely ionic and electrostatic, but the larger size of actinoid ions and their accessible higher oxidation states allow for some different structures. For instance, they can form monomeric tetrakas, cyclopentadenyl compounds like THsP4 and UCP4.
And you mentioned sandwich compounds.
Right, the actinosines, thoracine, THCH82, and the famous uranosine, UC8H2. These have the metal atoms sandwiched between two planar 8-membered cyclooctanoid rings. There's been a lot of theoretical interest in whether the actinoid 5 orbitals might actually participate in bonding to the rings in a unique way, possibly involving phi overlap, something not seen elsewhere.
Phi overlap. Wow. Okay. Now, briefly, what are the elements after uranium, like neptunium, plutonium, americium? We hear about them mainly in nuclear contexts.
Their chemistry gets even more complex, especially the redox behavior. Neptunium can readily exist in states from +3 to +6, even +7. Plutonium is notorious for its ability to have +3, +4, +5, and +6 states coexisting in solution under certain conditions, making its behavior very complicated to predict and control.
And americium.
With americium, the +3 state becomes dominant in solution, much like the lanthanoids. Am3+ is the most stable form, although +4, +5, and +6 states can be accessed. This trend towards +3 stability generally continues for the heavier actinoids.
And their impact. Obviously, nuclear power and weapons.
Critical roles there, yes. Uranium and plutonium are the primary fuels. But this also leads to the huge challenge of managing nuclear waste. Because many actinide isotopes have very long half-lives and are highly radiotoxic, safely containing them for thousands of years is essential. Techniques like vitrification incorporating the waste into stable glass or developing advanced ceramic waste forms like synrock are key research areas.
But there's a surprising everyday use, too. You mentioned smoke detectors.
Yes. It's quite remarkable. Many common household smoke detectors contain a tiny amount of americium-241, specifically Am241 oxide.
How does that work? Isn't americium dangerous?
Am241 is an alpha emitter. The alpha particles it releases are energetic ions, and inside the detector they ionize the air molecules in a small chamber, creating a steady electric current. If smoke particles enter the chamber, they interrupt this flow of ions, reducing the current. The detector senses this drop and triggers the alarm.
But is it safe to have in the house?
Yes, it's considered safe. The amount of Am241 is minuscule, and alpha particles have a very short range. They can't even penetrate a sheet of paper or the outer layer of skin. As long as the source remains sealed inside the detector, it poses no significant risk. It's a clever use of nuclear properties for safety.
That is genuinely surprising. So from obscure entries at the bottom of the table to phosphors, lasers, magnets, nuclear fuel, and even smoke detectors, these F-block elements are really woven into the fabric of our modern world.
Absolutely. We've seen the lanthanoids generally predictable, incredibly useful in materials science and technology due to their unique electronic structures. And then the actinoids, chemically diverse, dominated by radioactivity, fundamentally important for nuclear energy, but with their own surprising applications too. It all stems from how those electrons behave.
It really drives home why understanding even these seemingly obscure corners of the periodic table matters. Their properties impact the technology you use every day, the energy that powers your home, and even safety devices.
Couldn't agree more. They are far from just a chemical curiosity.
And thinking about the complexity here, the lanthanoid contraction, the diverse actinoid oxidation states, relativistic effects influencing properties, the theoretical nuances of orbital bonding. It really makes you pause.
It does. It makes you wonder, doesn't it? Considering all the intricate physics and chemistry at play in these heaviest elements, what other fundamental insights into matter are waiting to be discovered out there at the frontiers of the periodic table if we keep pushing our experimental and theoretical tools?
That's a fantastic thought to end on. What else might be hiding in plain sight within the atom? Well, thank you for joining us on this deep dive into the fascinating world of the F-block elements.
My pleasure.
Keep exploring, keep asking questions, and we hope you'll join us again next time on The Deep Dive.